Okay, this is an example of first order linear differential equation with initial condition. Now the reason we have an initial condition is because we normally ask to evaluate the value of the constant of integration once we have found the general solution of the differential equation. Now let me just remind you here that this equation is not in a standard form, and the standard form, let me just write it down here, dy dx plus p of x times y equal to q of x. Now remember, this is the standard form of the first order linear differential equation. If you compare one with this equation here, the standard form, we see that we need to rewrite it in this form by dividing through by x. So if we do that, then I'll have dy by dx plus 1 over x times y equal to 2, and the x cancels out with the x. Now this is what we call an initial condition, which basically means that when x equal to 1, y equal to 0. Let me just write that clearly. This is 1, which corresponds to the value of x, and this corresponds to the value of y when x equal to 1. So now let's identify what is p of x in order we find an integrating factor. Let's call that equation 2. So here our integrating factor mu of x is equal to e to the integral of p of x times dx. And if you compare equation 2 with the standard form, you will find that p of x is simply equal to 1 over x. So let's just do that. So e to the integral of 1 over x dx, which gives me e to the ln x, and this is simply equal to x. So our integrating factor is just equal to x. We now multiply equation 2 by our integrating factor x. So let's do that. That gives me x dy by dx plus y equal to 2x. And that's equation 3. Now if you notice that equation 3 is the same as equation 1, and that happens because the left hand side of equation 1 is an exact form anyway, so it doesn't really matter if you go back to the same equation, but we always try and identify or write the equation in the standard form to be able to identify p of x and find the integrating factor of mu of x. So we now, if you look at the left hand side of equation 3, it is really an exact form because this is simply d by dx of x times y, and on the right hand side equal to 2x. Now if you differentiate xy using the product rule, you will get back to the left hand side here. So hence we rewrote that left hand side expression into in this form. Now we can integrate both sides, so we'll have integral of dxy, and again I emphasize here this is just we integrating 1 times dxy equal to the integral of 2x dx, which gives me xy on the left hand side equal to x squared plus c. Now normally when you integrate x, you get x squared over 2, where the 2 cancel out with the 2 here, so it leaves me with this. Or we can rewrite y in terms of x to have y equal to x plus c over x. And this is what we call the general solution. So equation 4 is the general solution to the differential equation. We now going to apply the initial condition to this. So let's just keep this in here. So if we apply the initial condition, we have y of 1 equal to 0. So that implies that when x equal to 1, y equal to 0. So let's just do that. So on the left hand side I will have 0 equal to 1 plus c over 1, which is basically 0 equal to 1 plus c. So this gives me now that c equal to minus 1. So now we substitute the value of c into the general solution for, and this means that y equal to x minus 1 over x. And this is what we call a particular solution. And that's the end of this lesson.